Okay, hi, I'm Rupert Croft, and the organizers asked me to talk about this paper here. It's quite a simple idea. It's about whether we can use galaxy parallax to measure the Hubble constant. So as it's a simple idea, hopefully I won't spend more than 10 minutes on it. So here goes. So the idea of cosmic parallax and measuring parallax in expanding universe actually goes back to 1935. So here's William McCree. He wrote a paper in 1935 about all the different observable relations, luminosity distance, angular diameter distance, and so on. He included parallax in there for completeness, even though, of course, he recognized that it would be very difficult to measure. It also made it into the famous cosmology textbook by Stephen Weinberg. So this was in 1972. So the idea has been out there for a long time. Actually measuring it is obviously going to be very difficult. And one of the problems is that the small baseline we have to work with of the Earth going around the sun means measuring parallax on cosmological scales is tough. But there's an alternative. You can measure cosmic secular parallax. And basically there you would make use of the fact that the Earth is moving through space with respect to a frame defined by the cosmic microwave background. Basically, obviously, the Earth, most of that motion comes from the galaxy itself or the local group moving through space. You make use of that because it's about 350 kilometers per second over a 10-year span. That would be of order 1,000 astronomical units. And so 1,000 astronomical units means that for a given angular precision, you could see maybe 1,000 times further. Okay, so that is called cosmic secular parallax. Who came up with that first? It was the Russian astronomer Kardashev. He's more famous for his work on galactic civilizations, civilizations which could take over a whole solar system and then a whole galaxy and so on. He also had lots of other great ideas. Cosmic secular parallax was kind of a more mainstream idea, I guess. So even to him, of course, he said that there's very difficult to think about whether we'd be able to measure that. So basically, 40 years later, an undergraduate, Fiona Ding, seen here, worked with me on some paper just seeing what could be done with more modern instruments. For example, with Gaia, could we expect to measure anything with Gaia in astrometry? And with Gaia, you could try and look at point sources, quasars, and you might be able to measure Hubble constant with a signal to noise of maybe 3 from relatively nearby quasars. We also looked at whether you could constrain dark energy using Gaia and SIM and other astrometric satellites. And, there's some possibilities there. But, okay, we didn't go much further than that. More recently than that, Jenny Payne et al., just published last year, a first attempt to actually look for cosmic parallax using Gaia, not using quasars this time, using galaxies. And because Gaia only finds images of point sources, doesn't send back information for whole images, they had to use point sources that were detected in galaxies, so sometimes centered on galaxy nuclei, and try to use that to measure cosmic parallax. And they made an upper limit, although they weren't close to actually measuring the effect. They at least made an upper limit, and it was a first attempt. There's lots of interesting stuff in their paper. So what we like to do is use all the information in galaxies. So if we have a nearby galaxy, obviously there should be a lot more information than just a single point source. And if we could use information from all the resolved elements separately and average over them, maybe we could do really well and get a really precise measurement of the parallax shift of a galaxy, okay? And then just do that for nearby galaxies and hopefully measure the Hubble constant from the galaxy parallax. And so is that possible? And so I sort of had a look into this. And one of the secrets is you want to do image registration. So basically if you have images, so extended images, you want to line them up, and you should be able to try and measure what is the shift between two images. And you can actually do that to way below pixel resolution using modern techniques. And that's something here. There's some satellite images, but obviously you can do that with galaxies. And so I had a go at doing that, and I'll talk to you about that in a second. Okay, so what instruments and what observations could be useful for this? Well, you need a very large field of view to get nice images of many nearby galaxies, and luckily there are instruments coming along. For example, the Rubin and Rubin telescopes, which are going to have great data sets. They're going to be able to do amazing astrometry and hopefully do astrometry of galaxies. And so that was the idea, to try and simulate what they would see. Okay, so obviously also apart from nearby galaxies, you want to have a reference frame of galaxies that are very, very far away, that basically are not going to have a detectable parallax, because you want to measure relative shifts. Okay, that's the idea. You want to measure a relative parallax shift. And so that obviously those instruments are going to be able to measure, billions of galaxies over large fractions of the sky. Okay, so for the sort of test or the trial of how these things would work, I just made some mock galaxy catalogs, quite small ones out to redshift 0.05, so that's about 200 megaparsecs, using a nice publicly available simulation, a big simulation from Ishiyama et al. And I just made these, and they included galaxy positions and also velocities. The velocity field is an issue, obviously measuring the Hubble constant, as you know, from nearby galaxies, the peculiar velocities make a big difference. And so in this case, I wasn't going to model the velocity field in detail in the simulation. I just assumed that a velocity field model could be used to remove some of the component of the peculiar velocities, as people have done, but I assumed that there would be an error left of 100 kilometers per second, root mean square, in each galaxy velocity. That's sort of conservative if you look at what people have said they could do, but still, I didn't really test actually fitting a real velocity model or making a real velocity model. Okay, so what about the astrometric errors on the galaxies? Well, what is available obviously out there are not astrometric errors on galaxies, but on point sources. And so I had a look at the science requirements for LSST, and the error obviously depends on magnitude. When you get down to very faint point sources, the Poisson, the photon shot noise, actually brings up the astrometric error. And you can see that for very bright sources, about 0.2 milliarc seconds is basically what the LSST science requirement is, or maybe it's actually slightly better than that, but I chose 200 microarc seconds, 0.2 milliarc seconds for the fiducial value. And for the Roman Space Telescope, about 25 microarc seconds, which sounds amazingly good, so hopefully they can do that. That's in their science requirement for bright sources. Okay, so then what to do about extended sources? So I thought I would try taking observed images of galaxies from the Sloan Digital Sky Survey and from HST images, and then just see how well you could shift them by random amount, and then recover what that image shift is using image registration techniques. And so the image registration technique that I used was in Fourier space. You can do sub-pixel image registration, and there's a nice paper by Guizara et al. And there's making it easy. There's a nice AstroPy implementation. And so the idea is that you measure the cross-correlation function between two images. You measure the cross-correlation in Fourier space, then you zoom in on the peak, and then from the peak there, you can see on the right, you basically can get a sub-pixel, often very, very far below a pixel shift between the two images that you can find. And so the interesting thing was to do that for different galaxies with different numbers of resolution elements, to see if having a big galaxy, you could really average over those resolution elements and get a much better measured astrometric shift than you could do with a point source. And so you can see I tried different galaxies from Sloan and from Hubble Space Telescope. And so you can see the number of resolution elements along the bottom, so going all the way up to a few 100,000 resolution elements. And then up here is the astrometric error that you get from doing these experiments, shifting by a random amount, and then doing the image registration in Fourier space. And you can see basically that smaller galaxies with the less resolution elements have a bigger error on their position than the larger galaxies with more resolution elements. And in the paper, what I did is I assumed that the error on the position error, the astrometric error, would go down like 1 over the square root of the number of resolution elements. That would be the ideal case. And this experiment was to see how well that actually worked out in practice. And the 1 over square root of n is basically the dashed line, and the solid line is the best fit to the results from these example galaxies. And you can see that it's quite close. It was actually, instead of a slope of minus 0.5, it was a slope of about minus 0.44, I think, which was about 2 sigma away from the ideal value. So it basically looks like you can average over the resolution elements in individual galaxies and basically boost the precision of your measurement of astrometric shift of whole galaxies. And so having done that, basically I looked at the galaxy parallax shift in bins like you would do for a survey. And so at the bottom, the x-axis is redshift, goes out to 0.05, and you can see, so remember 0.05 is about 200 megaparsecs, and you can see that the parallax shift, basically this is per year, so basically in the secular parallax you get what looks like a proper motion, micro arc seconds per year, okay, as the Earth or the galaxy basically moves through space with respect to the cosmic rest frame. And you can see obviously nearby galaxies basically have a larger parallax shift than further away ones, and that's how you can basically tell their distance from this parallax shift. And the idea is to measure the Hubble constant. Basically the Hubble constant gives you a scaling of the theory line, the parallax distance here, which basically just scales up and down with the Hubble constant. And so to get the Hubble constant for a measurement like this, you would just fit the orange line to the points. And you can see this is for one example mock survey, for an LSST survey, and for one Roman high latitude survey. And you can see that the error bars are much smaller for Roman, and that's mostly because the astrometric errors for the space-based astrometry of Roman are significantly better. The sky error of the high latitude survey is actually obviously smaller than LSST, so the astrometric errors being smaller wins out there. Okay, so you can make many mock surveys and have a look to see what sort of error bar you would expect on the Hubble constant, and you can see the histogram here. Basically the perfect measurement of the Hubble constant H naught over the true H naught of 1 is here, and you can see that there's kind of spread out for LSST for the Rubin telescope with an RMS error of about 2.8%, and for the Roman telescope the error is a little bit less than 1%, the RMS error. So this is all for fiducial values based on the science requirements for those telescopes, and obviously also on the ideal situation where everything works out well and there's no additional sources of field distortions and all sorts of other things that if you probably know that Gaia has had lots of problems. Or okay, it's obviously an amazing instrument, but there have been some issues about the accuracy of the Gaia astrometry, and so it just shows that the astrometry is a very difficult thing. And so obviously this is just the ideal perfect case, and I'll come back to that in a second. Okay, so you can have a look at the percentage H0 error versus galaxy magnitude, and you can see here that you don't actually have to have very faint galaxies in order to do well, because the nearby very bright galaxies actually have lots of resolution elements, and so you can do pretty well even just looking at 16th magnitude galaxies, for example, and getting redshifts for those. Obviously you need redshift to do the parallax with redshift, and the numbers of galaxies wouldn't involve anything beyond what we have in current surveys, for example, like DESI and so on. And here the two colors of the lines, the blue and the orange, basically show you the difference between taking one measurement per galaxy and averaging over all the resolution elements in a galaxy. And so you can see that if you average over all the resolution elements, you definitely get a better precision on H0 than if you just do one measurement per galaxy, like if you were taking a point source at the center of each galaxy. So it's obviously worth basically averaging over the resolution elements and actually making use of that extended source information in the astrometry. Okay, and so here's I used the science requirements versions of the astrometric errors that I showed you in the graph before for bright point sources, and then obviously varying as a function of magnitude. And this is just how the precision on H0 would vary depending on changes to that. And so you can see that even if the astrometric error was significantly worse, say 0.1 milliarc seconds rather than 0.025, you would still get a 1% measurement supposedly with Roman, and you can see here again the two line colors. The blue one is where you only do one measurement per galaxy again, and this one is where you use all the independent resolution elements. And you can see that obviously the ground-based Rubin telescope has significantly worse fiducial astrometric point source error, and so even though there are more galaxies, it will be difficult to make a precise measurement of distance from galaxy parallax. Okay, so how realistic is all this? Obviously it sounds kind of far-fetched, and of course it would be tremendously difficult to do this. So the very brave first attempt that I talked about before by Payne et al., they tried looking at Gaia data release 2 data. Turns out that their upper limit they measured was 40 times the signal, instead of making a detection at the sort of 3 or 5 sigma level, which will be the sort of optimistic case of what you could do. It's possible, of course, that future data releases from Gaia they'll have better results with that, and hopefully they will. They're aiming to look for a detection. The galaxies that they're mostly looking at are mostly within 5 or 10 megaparsecs, and so it's not clear. That probably wouldn't give you any sort of constraint on H0, but it would be a detection of cosmic parallax. So basically, even detecting the parallax will be very difficult, let alone measuring H0 with precision. With the science requirement errors, as we've seen in the experiment in the mock catalogs I just showed you, we predict say 3% and 1% error on the Hubble constant, which that would be good if it was possible, but it seems very optimistic. But still, there's some things that can be done in the future. What we could do is try to do real astrometry with galaxies observed with the Hubble Space Telescope with different epochs. Also, JWST has got the same detectors as the Roman telescope. JWST will be launched very soon, and we could try to do some astrometry with JWST galaxies, and they would have some of the same detector scale level effects as would happen for the Roman Space Telescope. For example, things like charge transfer effects and field distortions and other things. So it will be good to look at the effects of those, and obviously there's a lot of work being done by the Rubin and Roman astrometry consortia looking at point sources, modeling those effects, right? And so it will be interesting to see how they propagate into the extended source astrometry. One positive thing you could do is actually go out further than redshift 0.05, which is where those mock catalogs I talked about are restricted to. You could, in principle, if you could measure out to 0.05, you could definitely go much further, and so that would increase the precision of your measurement and maybe take you further away from the regime of having peculiar velocities be important. But overall, it seems a bit far-fetched to think that we're going to cure the Hubble constant tension by using this, although in the far future it would be nice to make a purely parallax, purely geometrical measurement of the Hubble constant. And even without that, if we could just detect the effect of cosmic parallax, it would be a fun thing to do. Basically, if you had a cosmic parallax measurement like this, parallax of galaxies, we'd actually really be seeing the universe in 3 dimensions, right? We'd actually see that. We'd actually see the parallax shift of whole galaxies. And so that's definitely something to look forward to, and hopefully we'll be able to do it one day. Okay, thank you very much.